All right, everybody, good to see you all here. Hope everybody is doing all right. So the plan for this morning is we're going to be thinking about some applications and examples of Faraday's law. So last time on Monday, we saw what Faraday's law is, and we really just sketched out this example of a quite kind of theoretical electrical generator. So we just kind of got to somewhere where we saw we can move something in a magnetic field and get a voltage. So today, the plan is that we're going to be building on that, and we're going to be having a look at two super important examples in the electrical grid for making the whole thing work, so generators and transformers. So as well as seeing some important facts in a bit more detail about how these things work, hopefully this should also be a couple of very important examples of how Faraday's law works in practice. So we just saw Faraday's law for the first time on Monday. So hopefully by seeing a couple of ways where this kind of really works and we really need it in an applied situation, that should be helpful to understand Faraday's law in general. So that's the plan for what we're going to be thinking about today. Now let's start with where we got up to last time. We just had this very kind of schematic picture for what's going on with an electrical generator. So we had this magnetic field over here and this top-down view of magnetic coil, and we spun it around, changed the area, and that's what gave us this alternating voltage up here. Now, what I'd like to start by thinking about is this is the kind of basic sketch out of the relationship. So what we're going to be doing for the first part of the lecture today is really making this relationship a bit more concrete. So getting a bit more exact about what this is and then what we get for the voltage, so that we're able to calculate things. If we're thinking, okay, how much voltage do we need to get from a generator, we're able to calculate all of those things that we need. So that's what we're going to start by thinking about. So I got a question to get everybody thinking about this. If we're thinking about this area versus time graph here, what would we say is the functional form of the area versus time? Now, has anybody heard this term functional form before in terms of describing relationships? Okay, so just a couple. So this is actually a very important concept, especially physicists, we like to think about this a lot. So maybe we don't know exactly what the equation is for what's our area versus time. So, none of these are equalities. But what we're just interested in is what's the basic relationship between how we're changing with time and how the thing we're observing. That's what we mean by functional form. So we don't know exactly what it is. We're just thinking about what's the general form of the equation. So when we're thinking about our area versus time, or areas we're rotating the coil, which of these would we say is the functional form for how that varies with angle? So if you're not sure about this one, have a think about the area versus time. Think about what that area is when the angle is 0, when the time is 0. Which of these is going to give us that functional form for the area versus time? Okay, let's see what everybody thinks. What's the functional form of our area versus time? What's everybody think? Okay, so some people thinking about all of these. Looks like most people thinking could be A or B. So the general idea with this is that, we've got our area and it's a function of time. So there's going to be some area that the magnetic field can see against time. But, all of these, we're thinking there's some functions of angle. Now, looks like some people thinking maybe it could be C or D. Most people going for these more just the sinusoidal ones, so the cosine or the sine. Now, the key with this one is to think what's going to happen when our angle is 0. So when our angle is 0, we want the full area. We don't want the area to go to 0. So if we're thinking about these two, so what do we get for sine of 0? What's that going to be? Any thoughts? Yeah? Exactly. So sine of 0 just going to be 0. So we know it's got to be the cosine one. So I think everybody thinking along the right lines, but the correct answer is option A, the cosine one. So this is the functional form for how our area depends with the angle. So it's going to be a kind of cosine relationship. So the next step of this puzzle is to really get a bit more exact and not just have a kind of functional form, but work towards an exact equation for what our area versus time is. Now, to think about this and to get to this exactly, we need to think about this concept of phase in waves. Now, who's done phase before, kind of feeling solid with phase? Okay, so just a few people, not too many. So that's fine. So let's think about exactly what we mean when we're thinking about the phase of a function. So we've got our relationship here, so this time and area, and it's a cosine. So that's the functional form. But if we want to actually write down the equation for this, we need to relate what's going on with our time to exactly what we want to be putting into our cosine function. And to do that, we need to think about this, what we mean by the phase of something. So let's see exactly what's going on here. So if we look at the time, so we've got time on this axis here, we know that we're going to start over here at time 0. And the key thing which sets the scale is the time for one complete cycle of this cosine function. So we're thinking over here, we need to pin down what's the time going to be over here in terms of the frequency of how fast we're spinning our magnetic coil. So if we say, okay, the coil's rotating with a certain frequency, so maybe it's rotating 50 times a second, we know that it's got to complete one whole cycle in 1/50th of a second. So if we put the time over here, whatever the frequency we're rotating our coil at, we know that by the time we get over here, that time has got to be 1 over the frequency. So if we take that example of a 50 hertz rotation, that means it's got to complete a whole cycle in 1/50th of a second. So that really sets the scale for how fast this function has to happen. The other useful point to pin down is just what's going on in the middle of this function here. So if it's got to take a time of 1 over f for a whole cycle, then it's got to take a time of a half 1 over f for halfway through the cycle. So if you like, you can try this with some frequencies. So maybe try for 50 hertz, see what the time's going to be for a whole cycle, see what the time's going to be for half a cycle, or try for 60 hertz and see how much time we're going to get for one whole cycle of this. So this is how fast we've got to spin that magnetic coil. Now, if we're thinking about cosine functions, we can't actually put seconds, we can't feed a cosine function directly with time. We need to convert these times into some angles that the cosine function is going to be happy taking in and calculating. And that's really why we need this concept of phase. So let's unpack this in a bit more detail, because if we were just graphing this as a cosine function, this axis wouldn't be time, it would be angle. So let's see what the angle is, and we call the angle, that's what we really mean by phase. So how far we are along the wave in terms of the angle. So if we start over here, when our time's 0, our phase is just 0. So if you put 0 into your cosine function, you're just going to get the start of the function. So you're just going to get 1. And then once we've done a complete cycle, so we know what the time is in terms of the frequency, we say that that's a phase of 360 degrees because we've done one whole cycle. So this is a kind of generic property. Whenever we've got a wave, if we're saying the phase is 360 degrees, that means we've done one whole cycle of the wave. Now, in the case of this magnetic spinning around coil, there's a very direct correspondence between what we mean by the phase and what's going on here. Because if we say the phase is 360 degrees, it means this coil has spun around one whole revolution. So that's the basic idea of phase. You could probably guess what the phase is going to be when we're halfway through. When we're halfway through the phase, it's going to be 180 degrees. So we've just maybe taken the coil and flipped it halfway. So phase is what the cosine function thinks about. So if you want to evaluate something on a cosine function in your calculator, you know, you need to put in angles. You can't put in what's the cosine of 30 seconds. So your calculator is going to think that's, you're asking for the cosine of 30 degrees. So we need to get from these times in seconds up to something that the cosine function is going to be happier with. Now, the next thing we need to do with this, and the last thing before we're ready to kind of write this down as a complete function, is to think about this phase in terms of radians. So units for angles, not just degrees. Who's done radians before? Okay, same people as phase. Okay, so radians, they're just another way that we can measure angles. So, you know, here we've got the angle measured in degrees. Radians, you can just think of them as a different sort of system of units for measuring angles. And whenever we're thinking about cosine waves, frequency, all that kind of stuff, we always want to be measuring the phase in radians. Now, they might seem a bit unfamiliar, so let's just pin out these key points, see what they're going to be in radians. So if we start from the time of 0, the phase in radians, it's also just going to be 0 radians. So the phase in radians, 0 is just 0 in whatever units. Now, if we come all the way over here to one whole cycle, so our angle is 360 degrees, that's a kind of complete cycle. But the way radians are really defined, it's quite useful to think about sort of halfway. So if we have an angle of 180 degrees, does anybody know what that is in radians? Oh, yeah. Yeah, excellent. Very good. Very good, excellent. So radians are defined so that if we have pi radians, so 3.14 radians, that's going to give us 180 degrees. So the phase in radians is just pi radians. And it kind of does seem a bit weird, especially if this is the first time you're seeing it, you know, an angle in terms of pi. But that's just what it is. So then if we come all the way over here, a phase of 360 degrees, what's that going to be in radians? What's it going to be? 2 pi. Exactly right. Exactly right. So just twice as much. So a phase of 2 pi. Especially if you're seeing radians for the first time, they can be a bit confusing. Maybe we just prefer degrees. Once you've done a few calculations with them, you kind of get the hang of it. So what this table really sets out is if we have a particular time, so we're at some time in our cycle, so maybe we're at a time of equal to halfway through the frequency. We've got to get from a time of this up to a phase of pi radians. So that's what we want our function to do. Our function has to do this for us. So if we give our function a time of 1 over f, to put that into our cosine function, we need to convert that into a phase of 2 pi radians. Now that might seem a bit mathematical. Let's take a look at the sort of the actual example. Hopefully that might clear things up a bit. So we've got a few different options for what our area versus time could be in terms of the cosine function. So we know that the functional form, it's got to be a cosine. So these are all cosines. And the original amplitude, it's always just a. So they all have a in front of it. So really what we're thinking about is what goes into our cosine function. So if we know that we've got that relationship between the frequency that we're spinning our magnetic coil and the phase, which one of these relationships is going to give us that correct relationship between the time and the phase? So the thing that's really going to help you with this one is looking at this key point that when the time is 1 over f, the phase has to be 2 pi. So have a look at each of these. Which one will give us that correct result? That when we enter a time of 1 over f, it's going to give us a phase of 2 pi. All right, very good to see those responses coming in. Let's see what everybody thinks for this one. What's the actual equation that relates our area to our time? Okay, so some people thinking could be A, B, C, or D. Now, this is a bit of a tricky one, but the key thing here is this relationship here that when the time is 1 over f, we want our phase to just be 2 pi. So we can think about testing all of these. So if we take our time and set that equal to 1 over f, then that's just, and if we have our time there, then that will just cancel out. So if we actually inspect what's going on with all of these, what's actually going to give us this is this one over here, because if our time is equal to 1 over f, we have 1 over f times f, so that's going to cancel out, and we're just going to be left with the 2 pi over here. So correct answer is option C. So very well done, everybody, if you got option C, because it can be a bit tricky and it's very easy to get it the wrong way around. And to be honest with you guys, I get these kind of things the wrong way around and back to front all the time. So I really do have to kind of think them through. So don't worry too much if you kind of just get a little thing back to front. But yeah, correct answer is option C. Now this is a really useful equation, because what this allows us to do is, if we've been having our electrical generator running for a certain amount of time, we know exactly what the area of that coil is going to be in our magnetic flux. And this is exactly what we need to calculate the voltage that we're going to get from our generator. So maybe when you guys are graduating, maybe if you're working in an electrical power station, keeping an eye on the electrical grid, something like that, this is going to allow you to see exactly what the voltage is going to be at a particular point in time. So what we're going to do, let's take this relationship for our area versus time, and we can use Faraday's law to see what the voltage is going to be. So let's take a look at all the math here. Now, just a bit of a warning, there's quite a bit of math here, might look kind of scary. Let's just take things step by step, and hopefully not going to be too scary, okay? So we got this question here. What we're trying to do is use Faraday's law to go from the area that you guys just figured out, get back to the voltage. So let's take a look at all the pieces of the puzzle here. Let's see what we have. So we've got, this is our area, you guys just worked out, so area cosine 2 pi ft. And we know from last time, from Faraday's law, what the voltage is, how it relates to the area. So the area is equal to minus NB, so the number of coils of wire we have, that's the N, the B, strength of the magnetic field, and then dA by dt. So the derivative of our area with respect to time. Now, who's done derivatives before? Okay, so if you've done derivatives before, especially sines and cosines, this should be fairly straightforward. If you haven't done derivatives before, don't worry about it. We've actually got everything that we need right here to figure this one out. So the derivative is just asking what's the slope at every point in time, and we can use this expression here. So if we're saying, okay, what's the derivative of cosine theta with respect to theta? It's just going to equal to minus sine theta. And if there's anything in front of the theta, so an x, that thing in front of the theta just goes in front of the minus sign. So if we're looking at our area, we're taking the derivative with respect to time, think about what the thing in front of it is. So even if you haven't seen derivatives before, or not derivatives of sines and cosines, we've got everything we need here to put all of the pieces of the puzzle together. So I'll give you guys a bit of time to have a think about this one, see what you get. What's our voltage versus time going to be? Which of these options is it? If you haven't seen any calculus before, we've got everything we need here to figure this one out. You know, we know that the derivative of cosine x theta with respect to theta, it's just minus x sine x theta. So really what this question is about is identifying what corresponds to that x part in our area versus time, and then applying that rule for what the derivative is. So have a go with that, see which of these is the correct option. Okay, very good to see those responses coming in. Very well done, everybody, working through that calculus there. Let's see what everybody thinks for this one. Okay, so some people thinking could be all of them. Actually, let me just move that code out the way, because we need to see what all of these are. Let me just get the code out the way. There we go, got the code out the way. Now, this can be a bit of a tricky one because there's a few pieces of the puzzle going on here. So we're starting with a cosine function. And we know from this rule here that if we start from a cosine function, it's going to get turned into a sine function. So it's got to be one of these ones which is a sine function. So either this one or this one. So we can narrow it down. It's either got to be A or D. And then really what's going on here is with this 2 pi f business. So if there's something in front of the derivative, so an x here, we just take it out in front. So the thing in front here, it's the 2 pi f, so it just goes in front. So what that's going to give us is option D over there. So very well done, everybody who gave this one a go. Like I said, yeah, got a.
I don't understand where the 2πf at the very beginning comes from.
At the very beginning, the question was, where's the 2πf coming from? Yeah. So where this comes from? Okay, great question. So if we think about, we've got our function here, the derivative of cosine x theta with respect to theta is equal to all this stuff. So in our situation, we're taking the derivative of this area with respect to time. Maybe I wasn't super clear on that actually. So we're taking the derivative of this area with respect to time. So the thing we're taking the derivative with respect to is t. So the thing in front of the t is this 2πf. So that's the thing in front. So that's what's going to get moved to the front of the sign. Does that clear things up? I'm sorry, I wasn't very clear with the t, and I'll know for next time. Thank you for asking that. Clears it up. Great question, actually. Does anyone else have any other questions about this? Okay, so this is actually a really useful result, because what this tells us is what our voltage is against time in terms of, the frequency of our generator, and then how we've built our generator. So how big the coil is, how strong the magnetic field is, and how many loops of wire we have in our generator. So I know quite a bit of work to get here, can seem a bit tricky. So let's just take one slide, put everything together, and recap everything that we've seen so far about this. So the picture here, we had, this is a very kind of rudimentary electrical generator, right? We've got a kind of coil and it's sitting in a magnetic field, and we've just got, someone, and they're just sitting there all day turning the electrical generator, okay? So clearly if you're, building a power station, this is not going to be a very good, I suppose at the best it's a kind of carbon neutral way of generating electricity. But yeah, you want to turn this into a wind turbine or a steam turbine, something like that. But fundamentally, this is what's going on with an electrical generator. So if we have n coils of wire, so here we've only really just got one coil of wire, but you want to wrap as many coils of wire as you can fit around your generator. So the magnetic flux is the number of coils of wire, how strong your magnetic field is, and the area of the coil. So here, it's a square. Sometimes that coil could be a different shape, could be a circle, something like that. It's just what that area is. So then we know from Faraday's law that voltage is minus the rate of change of this flux with respect to time. So we know what the flux is, and however we're changing the flux, this is the relationship between what that changes and the voltage. So maybe we're changing the flux by changing the magnetic field, you could do that, or the easiest thing, as we've just seen, is to change the area. So what that gives us is this voltage here that we just worked out. So our voltage, it's equal to some maximum voltage times sine 2π(f)t. And this maximum voltage, it's equal to this business that we just saw from the derivative. So it's equal to the original stuff, so the NBA, and then we get the 2πf from taking the derivative. So these are all the pieces that we need to work out the voltage that we're going to get from a generator. Now, if we are making a kind of real generator in a power grid, very often what we want to do is increase the voltage when we're transmitting it and then drop it back down when it gets into the walls. So, with an electrical generator in a big power station, could be making tens of thousands of volts. And then when we're transmitting it, maybe transmitting 100,000 volts. But then, what comes out of the wall, you wouldn't want to plug in your laptop or your phone charger and get 100,000 volts out of the wall. So let's just take a bit of a look at what's going on with the electrical grid, why we're changing the voltage all over the place, what's going on there. So typically, in a power station, we might be getting 10,000, in this example here, 12,000 volts coming out of the the power station. Does anybody know why we want to increase the voltage if we're transmitting it over long distances? Oh, yeah.
Is it because there's less resistance?
Yeah, absolutely right. There's less resistance. So if we're transmitting, miles and miles over some high power cables, we don't want to be losing all this electricity that we've generated in thermal energy. So we step it up to a very high voltage, 400,000 volts, hundreds of thousands of volts. The electricity can travel miles and miles, and then it gets to somewhere a bit more regional, and we lower the voltage back down. Okay, so it goes down to 10,000 again, and then 240 volts into our house. Have you guys seen, if you look around, you can see electrical substations, stuff like this, and they're all, danger, high voltage, don't enter. So that's what's going on there. They're stepping down the electricity from this really high voltage into something that can go into your house. And the way this is done is with an electrical transformer. So that's what's going on in these substations here. That's what's changing the voltage. So transformers, they're an essential part of the electrical grid. We need them to raise and lower the voltage when we're transmitting electricity. And also, a very important example of Faraday's law. So for the rest of the lecture today, we're going to be looking at transformers, seeing how they work, seeing how they do this important part of the electrical grid for us. Now, unfortunately, we're not going to be thinking about the cool, robot transformers. We're going to be thinking about the slightly more mundane, everyday, day-to-day transformers. So they actually look a bit more like this. Who's seen transformers before? Anyone who's studied transformers before? Okay. So where did you guys study transformers before? High school. And was that in electronics, something like that?
No, it was in physics.
Okay, in physics. Okay, fine. So there's quite a few different ways you can approach transformers. It's one of these ones where you get quite a nice simple equation out of it, but it's important for us that we understand a bit more what's going on with the physics, because it's a very important example of Faraday's law. So just to give you guys a quick overview of what's going on here, a transformer, it's basically a big old lump of magnetic metal. And on one side, you connect it to your circuit by wrapping a certain number of loops of wire around it. And then on the other side, you wrap a different number of loops of wire, and then you connect that to the other part of your circuit. And as we're going to see, the reason you do this is because how you've wrapped, the number of wraps of wire you put around the transformer, that's going to affect the voltage that you get out of the transformer. So very schematically, if we apply voltage over here and change the voltage, so put it in that sinusoidal voltage, all these loops of wire are going to create a magnetic field in the transformer. And then if we come over to the other side of the transformer, that changing magnetic field, it's going to interact with all these loops of wire, and it's going to give us a voltage out the other side of the transformer. So that's the basic idea what's going on with the transformer. Let's take a bit of a look at the maths, see what is going on exactly, okay? So the two equations that we really need. So we need Faraday's law, we've seen this a couple of times now, so voltage minus the derivative of the magnetic flux with respect to time. And the magnetic flux, so it's the flux intensity, that B there, times the area, times N, the number of loops of wire. Now, in the transformer, we're not changing the area because that's fixed with how we've made the transformer. So once you've made the transformer, the only thing you can really change is, you can how many loops of wire you've wrapped around it. So let's think about, in this question over here, okay? So we know what the magnetic flux is, and we know how that's related to the voltage. But the only thing we're changing in the transformer is the magnetic flux density. So B is the only thing we're changing. So if that's the only thing we're changing, we're not changing A. A is just fixed now. What's going to be our voltage versus time in the transformer? If you're not sure about this one, it's actually exactly the same idea as we saw with the electrical generator. It's just in the generator, we were keeping the number of loops of wire fixed and changing the area. Now we're keeping the area fixed and the number of wires fixed, and we are just changing the magnetic field intensity. So see which one of those is going to give us that correct voltage versus time if we're only changing the magnetic field intensity. Okay, very good. See those responses coming in. Let's see what everybody thinks for this one. What's our voltage versus time? All right, okay, nobody going for C and D. People thinking it's got to be A or B over here. Now I can see what you might be thinking about with this option over here, because it's the change in magnetic flux, and the flux is the NBA. But we're keeping in the transformer, we're keeping the N constant, and we're keeping the A constant. So if you've done some calculus before, we can just kind of pull them out the front of the derivative because they're not changing. The only thing we're changing is the B over here. So what that actually gives us is this equation over here, option B. That's what we get if we're only changing the magnetic field intensity. Okay, so very well done, everybody who gave that question a go. This is what the voltage is in the transformer if we're just changing the magnetic field. Now, last slide for today, let's just do a bit of an overview of everything that's going on in the transformer, put all these pieces of the puzzle together, and see exactly what we're going to get out of a transformer. Okay, so let's go back to that picture, see everything that's going on here. So we've got the voltage, we've got the magnetic flux, and you guys just figured out if we're only changing the magnetic field, what we get is the voltage is equal to N times A times dB by dt. So what you guys just figured out. And I've put the little subscripts here for the secondary coil, because when we're thinking about a transformer, we talk about the primary coil over here, that's what goes in, and then the secondary coil, that's what comes out of the transformer. So if we're only changing the magnetic flux, then the voltage that we get out of our secondary coil, it's just the number of pieces of wire that we've wrapped around times the area, that cross-sectional area, and then the rate of change of the magnetic field. Now we can actually do the same idea on the primary coil side of the transformer, but just in terms of the voltage that's going in. So we can do exactly the same relationship that you guys just worked through, and for the primary coil we get the primary voltage, it's equal to the number of wires on the primary side times the area times the rate of change of the magnetic field. The difference on the primary side is that we're going to be inputting the voltage, and that's going to be causing the magnetic field to change. But the equation describing the relationship is the same. So we've got these two things on either side of the transformer, and we can do a little bit of algebra, and this is where things get really interesting. So if we do a bit of algebra on this side, we can solve for the ratio of our primary voltage to the number of coils of wire on the primary side. And what do we get? We get minus A dB by dt. So it's quite a nice relationship. Let's see what we get over on the secondary coil for the same thing. Let's see what we get when we do the same rearranging. So if you're following along in your notes, you can work through the algebra. Let's see what we're going to get for the ratio of the secondary voltage to the number of coils over here. So what do we get? Minus A dB by dt. Oh, now this is kind of interesting, right? Because the right-hand side of both of these equations is the same. We get that they both equal to minus area times dB by dt. So what this allows us to do is bring both of these sides of both of these two equations together, because we know that they both equal the same thing. We get this really neat relationship here. So we know that the ratio of the primary voltage to the number of loops of wire on the primary side, it's equal to the same thing on the secondary side. So after all that math that we've been doing all day today and all week, with Faraday's law and magnetic flux, what it all boils down to is this really nice relationship over here. So for example, if we said, we're going to get 10,000 volts from a substation and we want to get 240 volts out of the wall, we know what these are. We can work out what our ratio is for the number of primary coils of wire that we get to the secondary coils of wire. So really useful relationship if you're thinking about the right kind of transformer to use in a situation, or maybe if you've got a transformer and you're putting a voltage in, you're going to know what you're going to get out of the transformer. So that's just a big picture overview of what's going on with transformers. That's all for this week about Faraday's law, electromagnetic induction. Next week, we're going to be starting thinking about electrons in a bit more detail and the actual energy in electrons, and also what's going on with the physics of photons. So that's the plan for Monday. Hope everybody has a great weekend, and I'll see you guys next week.